multiple ways to simulate fluids. In a previous video, we simulated fluids by solving the Navier-Stokes equations using the stable fluids algorithm by Stam. A completely different approach is to instead model fluids as a lattice gas. In this video, we will explore one such method known as the Lattice Boltzmann Method, applying it to simulate interesting physical phenomena such as flow past different geometries, different modes of convection, and multiphase flow. The Lattice Boltzmann method is rooted in statistical mechanics principles. To understand its foundation, we first derived a Boltzmann distribution, starting with the concept of entropy. Entropy is the measure of disorder in a system. For example, solid crystals have low entropy due to their highly ordered structure, whereas liquids, which are capable of accessing more microscopic configurations, are considered to have high entropy. The Gibbs entropy equation expresses entropy S as a function of a probability distribution, F, of a system occupying particular states. The second law of thermodynamics states that at equilibrium, entropy is maximized in an isolated system. The probability distribution which maximizes entropy is known as the Boltzmann distribution. Note how at low temperatures, most molecules are clustered around low speeds, whereas at high temperatures, molecules have a higher average speed but have a more spread out distribution. This spreading out of the distribution reflects the increase in entropy, as the system can access a significantly larger number of microscopic states at higher energy levels. Importantly, the velocity distribution follows the mass and conservation laws shown below. How does velocity distribution evolve over time? The Boltzmann transport equation states that they evolve with neighboring collisions. Notably, omega, known as the collision operator, is notoriously difficult to solve. This is shown below for a two-body collision. Fortunately, we can employ the BGK approximation, which states that the distribution F should tend towards an equilibrium distribution at a rate determined by the relaxation time tau. This approximation holds true for low Mach numbers. Discretizing all equations over velocity space, physical space, and time, we arrive at the Lattice-Boltzmann equation. We can perform a weighted Taylor expansion of the equilibrium distribution function, derived earlier, with a now discretized velocity grid. Note that we define discrete particle velocities, Ci, and weights, Wi, by the following grid, known as D2Q9. We can calculate density and velocity from discretized conservation equations. The Lattice-Boltzmann method consists of two steps. First, collision from neighboring cells. Second, streaming or propagation of the distribution to neighboring cells. In a wind tunnel, there are three boundaries to consider. At the walls, we simply reflect the velocity distributions according to the discrete particle velocity directions. At the inlet, we need to apply special boundary conditions to ensure that the velocity is equal to the specified wind speed. From the conservation equations, we can write the following. Solving the system of equations for the wall density and unknown values F1, F5, and F6, we find the following relations. The third boundary condition is to specify an outlet for mass conservation within the simulation cell. In particular, flux on the outer edges is set to 0. By setting distributions F equal to each other. We first look at flow past a cylinder. At low wind speeds, velocity fields are relatively uniform, with the fluid flowing smoothly across the edges. When wind speed is increased past a threshold, around a Reynolds number of 60, regular oscillations start to form in the wake of the cylinder. This well-documented phenomenon is known as vortex shedding. The oscillation is so well behaved at low Reynolds numbers that there's a formula that can be used to determine its frequency. However, this behavior is not limited to cylinders, as we find that it also happens for flow past rectangular geometries. When several cylinders or boxes are placed in a wind tunnel, oscillations constructively interfere and increase the relative velocity amplitude, even at low Reynolds numbers. This is a known problem for skyscrapers placed close together. To mitigate this effect, engineers often create hollow floors, use mechanical dampeners, or use helical strakes to break up vortices. The next phenomena we can observe is the aerodynamic stall. While fluid flows smoothly over the airfoil's optimized shape at low angles, increasing the angle of attack introduces an adverse pressure gradient along the upper surface. This gradient forces the boundary layer to detach, a process known as flow separation. Once separated, the flow no longer follows the wing's contour, instead breaking down into a chaotic wake of turbulent swirls. These vortices dissipate the energy required for lift and significantly increase pressure drag. In both real-world applications and our simulation, reaching a threshold, typically around 15 degrees, causes this turbulence to dominate the upper surface, resulting in a sudden loss of lift, the stall. A common benchmark for fluid simulations is lid-driven cavity flow. In this setup, a fluid is contained within a square simulation box with 4 solid walls. While the 3 bottom walls remain stationary, the top lid moves at a constant velocity to the right. As the simulation runs, the moving lid acts like a conveyor belt, pulling the top layer of fluid along with it. This motion eventually spreads through the whole box, creating a massive slow-motion whirlpool in the center. This effect has many industrial applications, such as flow in polymer processing and modeling structural vibrations in aircraft bomb bays. Our simulation is currently lacking temperature. To model this effect, we need to introduce a second distribution function, g, of the same form as the velocity distribution, f. The only difference is the conservation equation, where the integral over g gives temperature rather than density. To build some physical intuition, let's start with a simple question. Why does smoke go up? This is because the density of hot smoke is lighter than that of the surrounding cold air, so buoyancy forces push it upwards. We can say that density has a linear dependence on temperature using the following relation. If gravitational body force has the following form, we can find the buoyancy force through a simple rearrangement. Instead of a simple weighted sum of the velocity distribution, velocity now depends on this buoyancy force by the following equation. The velocity distribution is updated by a similar equation as before, but now has the source term SI, which applies the buoyancy force. The equilibrium temperature distribution is updated the same way, without this source term. A new boundary condition is the zero gradient for temperature, given by the following formula, where Cw is the wall temperature. With this extension to our framework, we can now model thermally coupled flows, where fluid motion and temperature interact. A classic example of this is convection cells. If you ever boiled a thick liquid like soup, you might notice cell-like patterns forming in the fluid over time. These patterns arise because hotter, less dense fluid rises, while cooler, denser fluid sinks. This organized motion leads to circulating structures called convection or Bernard cells. To simulate this, we initialize a box where the top wall is cold and the bottom wall is hot, creating a vertical temperature gradient. The fluid in the box responds to this temperature difference. Warm fluid rises from the bottom, cold fluid sinks from the top, and a convective circulation develops. The onset and behavior of these convection patterns are controlled by the dimensionless Rayleigh number, which quantifies the strength of buoyancy-driven flow compared to viscous damping and thermal diffusion. It is given by the following equation. At low Rayleigh numbers, heat just slowly seeps through this liquid without moving it, a process called diffusion. But as we crank up the Rayleigh number, the buoyancy becomes too strong for the fluid to resist. It breaks out into organized circular patterns called convection cells. At even higher values, these neat patterns shatter into violent chaotic flumes, showing the transition from a calm flow to total turbulence. We can also model the rising of a thermal bubble by starting with a sphere of hot uniform temperature in a surrounding cold fluid. Because the hot fluid is less dense, it immediately rises. However, it doesn't stay a sphere for long. As it climbs, friction from the cold air peels the edges back, curling the bubble into a distinctive mushroom-shaped cloud. Note that the Rayleigh number controls the speed at which the bubble rises in the simulation. We can model smoke rising by initializing a small square held at a constant hot temperature in the cold fluid. Similar to the rising bubble, we see that smoke rises steadily with turbulence caused by random noise in the small temperature source. Even more interesting is the case of forced convection. By placing heated geometries into a wind tunnel of cool, moving fluid, we can simulate the cooling mechanisms used in real-world shell and tube heat exchangers. When the fluid hits a single hot cylinder, it initially creates an unsteady swirling wake. Over time, this settles into a pattern where the fluid directly behind the cylinder becomes a heat trap, carrying a steady plume of thermal energy downstream. However, when we introduce multiple cylinders, the physics becomes much more complex. The wakes are forced to bend and weave around each other, creating an interference pattern that changes how heat is stripped away from the surfaces. By replacing cylinders with rectangular blocks, we can simulate the thermal behavior of CPU heatsink fins. With a small number of fins, fluid flows freely between them, creating distinct wakes similar to the cylinder arrays. However, as we pack the fins closer together, the physics changes. The increased surface area creates more drag, forcing the air into a smoother parabolic velocity profile, similar to flow through a narrow pipe. Finally, we can simulate passive cooling or melting by allowing the heated objects to cool naturally, rather than maintaining a constant temperature. For a cylinder, the back cools faster than the front because the swirling vortices behind act like a pump, constantly pulling in fresh cool fluid. In contrast, the flat face of a box creates a dead zone of trapped air, causing the front to cool differently. Most interestingly, in a group of cylinders, the middle cylinder stays hot the longest. This is because it's shielded by the cylinders around it. The flow is so slowed down by the constant interference and vortex shedding from its neighbors that there is no fresh air left to carry its heat away. The last extension to the model is multiphase flow using the Shan-Chen model, which introduces an interaction force between multiple phases. This force is determined by the gradient of the effective density and is given by the following equation. And G is the interaction strength between the phases, given by the following. When discretized for a single component on a lattice, we calculate the force by summing over the neighboring nodes. This mathematical framework allows us to simulate the complex dynamics of a droplet impacting a pool of water. As a droplet hits the surface, the momentum transfer creates a central valley, flanked by rising peaks. These peaks travel outward as capillary waves, driven by a balance of surface tension and inertia. Eventually, viscous forces cause these disturbances to diffuse, as the system returns to its equilibrium state. While this simulation captures the core physics, observing the iconic water droplet crown requires a much higher viscosity of the fluid. In our current implementation, we're reaching the stability limits of the BJK approximation because this model is optimized for low Mach numbers and specific Reynolds ranges. Pushing the viscosity or velocity higher can lead to numerical instability. To summarize, we've explored how the Lattice Boltzmann Method serves as a powerful framework for simulating complex physics patterns around intricate geometries to the nuances of natural and forced convection, and finally, the dynamics of multiphase flow using the Shan-Chen model. The complete Python source code for every simulation shown in the video is available in the description below. This project involved a significant amount of research and rendering time. If you found this breakdown helpful or interesting, please consider liking, sharing, and subscribing to help the channel grow. Thanks for watching, and I'll see you in the next one.